Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and the Robert Board Center for Cyber Physical Systems IISc. Today's talk is by Gauri Joshi and she will be speaking about heterogeneity-aware algorithms for federated optimization. Gauri Joshi is an associate professor in the ECE department at the Carnegie Mellon University. Gauri completed her PhD from MIT WCS and completed her undergrad in electrical engineering from IIT Bombay. Her current research is on designing algorithms for federated learning, distributed optimization, and parallel computing. Her awards and honors include being named as one of the MIT Technology Review's 35 Innovators Under 35, the NSF Career Award, the ACM Sigmetrics Best Paper Award, Best Thesis Prize in Computer Science at MIT, and Institute Gold Medal of IIT Bombay. Before we move on to the talk, we request the online audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, you may unmute yourself and ask Professor Joshi directly or type them in the chat box, and we will relay your questions. Over to you, Professor Joshi.
Good evening, everyone. Thank you very much to the organizers for the invitation and the generous introduction. It is a pleasure to be here remotely. Today, I'm delighted to present my group's work on heterogeneity-aware algorithms for federated learning. In this talk, I'm going to cover snippets of several different works, and all of this research is joint work with my students who are listed here, as well as other collaborators at Carnegie Mellon and at Google. I will also mention some ongoing work during the talk. So when I say designing algorithms for distributed or federated learning, what I mean is algorithms to do stochastic gradient descent in machine learning. So as all of you might know, machine learning training today is synonymous with using SGD. It is the most commonly applied optimization algorithm. For example, the backpropagation algorithm used for training neural networks is a special case and a more efficient version of SGD. So at its core, SGD is a very simple algorithm. It involves optimizing or minimizing an objective function, such as the one illustrated here. So the objective function is generally denoted by f of x, which is equal to the empirical risk function, that is the average of the per sample losses at different points in the training data set. So here capital N is the number of points in the training data set, and small f denotes the per sample loss at the nth point. X here denotes the parameter vector, which consists of, say, the weights and the biases of a neural network if you're training that, or the parameters of any other model that is being trained. So in every step of SGD, the way the parameters X are updated is that you start off with the current version and then compute gradients of f of x, a noisy version of the gradient, by sampling a batch of B samples from the training dataset, computing the per sample gradients for them and averaging them, and applying a small step size eta to the gradient, and then taking a step in the direction of steepest descent. So as you can see from this update equation, SGD is inherently sequential. And for large data sets, running this iterative or sequential algorithm at a single node can be prohibitively slow. So in practice, it is imperative to distribute this computation across multiple nodes, that is, divide the task of gradient computation and aggregation. So in most state-of-the-art implementations of machine learning training, the task of computing gradients and updating the model is divided across a parameter server, which is shown here, and a system of M workers, which are servers in the cloud or edge devices or virtual machines, etc. And because the training data set is large, it is shuffled and then partitioned across these worker nodes. So each worker node has a partition of the training data that is stored at its local memory. And in every iteration, these workers will read the current version of the model from the parameter server. They will compute gradients of one mini batch sampled from their local dataset partition. And then the parameter server will aggregate these gradients as shown here to update the model parameters. And then this process repeats in every iteration. So ideally, if you use this setup, one would think that if you have more workers, then we should be able to process more data per iteration and hence get a m-fold speed up in training. But in practice, you don't get that ideal speed up because there are synchronization delays in waiting for all the workers to finish, or communication limitations on this link between the parameter server and the workers, and so on. So in the past few years, there have been extensive research on algorithms to improve the scalability of this framework, including some of our work on asynchronous SGD, local update SGD, overlapping communication computation, and so on. So I'm not going to go into these works today because today's talk is on federated learning and heterogeneity in federated learning. But I want to mention that these works are quite successful in improving the scalability of the parameter server framework. However, in spite of these improvements, this framework itself has some limitations. So the first limitation is that the worker nodes that I'm showing here are typically considered as homogeneous, and they're available throughout training and always connected to the parameter server. And this does not hold in practice, especially when the worker nodes are edge devices like mobile phones or sensors, tablets, etc. And more importantly, this training paradigm assumes that there is a centrally available data set which can be shuffled and then uniformly partitioned across these worker nodes. And this assumption, both of these, fail in many modern applications where massive amounts of training data is collected by edge devices like cell phones and sensors, etc. An example application of this is the next word prediction service, which is used on many smartphone keyboards. So here, whenever we type something on our phone, there is an underlying machine learning model that predicts and suggests the next word that we might type. And language models are used to make those predictions. So these language models are trained using the data which in this case is what the users are typing on their phones. So in order for us to use the parameter server framework to train these kind of models, we would have to send all the training data from thousands of edge devices to the cloud. And these devices are resource limited, they are bandwidth limited. So transferring all the data to the cloud can be very expensive and slow. And moreover, as you can see in this application, the data itself can contain private or sensitive information. So privacy laws often forbid sharing these data with foreign cloud servers. So these are some of the challenges when data collection itself happens at the edge. And federated learning is a new and emerging machine learning paradigm that operates within these constraints and still aims to collaboratively train models using data collected by edge devices. So the core idea of federated learning is that the data stays on the device, it doesn't move to the cloud, but model training is moved to the edge. So what happens is that in each round of training, these edge devices, they will read the current version of the model from the cloud. They will do a few iterations of local stochastic gradient descent using their own data. And then these updates will be aggregated by the server. and the model in the cloud is updated. So this process repeats in every communication round. So what you can see from this picture and this algorithm is that whatever is transferred here between the cloud and the edge clients is only the model. The data, raw data is not transferred between them. So because the data stays on the device, this paradigm offers better communication efficiency in many cases, as well as better privacy guarantees than just sharing data with the cloud. So that is the high-level idea of federated learning. Now let me make it more concrete by defining the objective function and the notation. So in the rest of the talk, we will consider a system of M edge clients, which are denoted by these mobile devices. And each edge client has a local objective function, fi of x, which is the empirical risk loss function computed on its own local data set. So di here denotes the local data set that is collected by the ith edge client. Now, these local objective functions are different from each other because the data sets are collected independently by them. And our goal is to minimize a weighted average of these local objective functions. So the global objective function f of x is equal to the weighted sum of these local objectives. And this weighted sum is taken in proportion to the sizes of the data sets at each of these clients. So the PI here is typically chosen as the fraction of data at the ith client. And the reason for this is that this tries to emulate the centralized training framework, where hypothetically, if we had sent all the data to the cloud, then the proportion or the weight given to the ith client would be equal to this PI. But there are other variants of this objective function where PI can be chosen in different ways. So the goal of the standard federated learning framework is to find the model X that minimizes this global objective function f of x. And you might think, how is it that we are only training one model and that model will be used for all the devices? Why not train personalized models? So that's a valid point. Like, instead of just training one model, you could train a customized or a personalized model that works better for each edge device. And there are variants of the setup that I'm going to describe that does that. But for the purpose of this talk, I'm going to focus on this single model case, which is the baseline federated averaging algorithm. So our goal now is to just train one single model that minimizes this objective function. Right. So this is the objective function.
Can I ask a question?
Yes, go ahead.
So in the previous slide, maybe I didn't quite catch this. So the X is the unknown which you want to find, right?
Mm-hmm.
And at each device I, or whatever, like at each edge I, you observe fx semicolon psi, or is the what is your observation? I didn't quite understand.
So at each edge device, you have this data set di. Mm-hmm. So you know this objective function fi of x.
So for each x, I'm able to evaluate this somehow. That's what it's saying. For if you give me any x, because this data set, somehow I know this f of x psi.
Yeah. So for each given x, you can compute this local objective function.
So I'm struggling with this to understand, what would be an example of this. So what you get to observe is psi. I mean, okay, this psi in the set di, but then you also know this f of x comma psi at each edge.
Yeah, so each edge client knows their own data set di, so they can compute this entire function locally. and they can optimize this entire function, but they don't know each other's xi. So this client does not know this f.
I see. Now I understood. Thank you.
Yeah, they know only their own data and their own objective function. Does that answer your question?
Yes, I understood. Thank you.
Okay, thanks. So let me now describe the basic algorithm. If we want to naively optimize the federated learning objective function, we would transfer all the data to the cloud, but we don't want to do that, right? So, and we also want to save the communication cost. So in practice, the algorithm that is used is that each of these edge clients performs tau local steps of gradient descent and shares the resulting model with the parameter server. So in every communication round, the current model is sent to the clients. These clients do some local updates using their data. And the number of local updates is denoted by tau. And then the resulting models, which can be different now because the data sets are different, are sent back to the central server, which aggregates them in proportion of the data set sizes at the different clients. So this is the algorithm, which is also called the Fed averaging algorithm, and this is widely used in practical implementations. So the goal of this talk is to understand how this algorithm is affected by heterogeneity in the system. And what do I mean by heterogeneity? There are actually several sources of heterogeneity in federated learning. The first source of heterogeneity is data heterogeneity. So these data sets that induce the local objective functions f1 to fm being different, because they are different as these edge clients take more and more local steps of SGD, their models will drift away from each other. And because of this drift, we can get an error in the aggregated model X, as we'll see more concretely in the next few slides. So this is the first source of heterogeneity. The second source of heterogeneity is communication heterogeneity. So typically there are thousands or potentially even millions of these edge devices. And at any given time, all of these devices may not be available. So often the devices are available for training only when they are plugged in for charging and they have a stable internet connection, which may vary across times of the day and also across time zones. So it is impractical to expect everybody to be available. So in practice, only a small fraction C of these clients is available at a given time. And this is called partial client participation. In every round, you just choose among the available clients and then use only those clients to do the federated averaging algorithm and update the global model. And the rest of the devices don't participate in that round. Whenever they participate, they get the new version of the model, then they do local training and then send it back. So this kind of heterogeneity in terms of communication or client participation exacerbates the effect of data heterogeneity. So in this talk, we'll also discuss some methods to tackle this source of heterogeneity. And then the third source of heterogeneity is computational heterogeneity. So the edge clients that I'm showing here may have different computation speeds and memory. So instead of forcing all of them to do the same number of local updates, it may be better to allow them to do variable numbers of updates depending on their computation capabilities. And moreover, these clients may also choose to use different local learning rates or local optimizers such as momentum or adaptive optimizers. And these variations across the clients and the local updates and the local optimization can cause some issues in terms of the convergence. So we are going to see how each of these sources individually and also combined affect the error and the convergence of the Fed averaging algorithm. So that's the high-level goal of the talk. Any other questions at this point before we move on?
I think it's clear.
Okay,
Yes.
sounds good. So let me start off with talking about data heterogeneity. And let us first try to understand what I mean by it, like why is this a problem? So to understand that, let's consider a toy example. So suppose XT, as shown here, is the current version of the global model. And X star is the global optimum. Let's assume that there's only one unique global optimum, which minimizes that f of x, the averaged or the global objective function. And because the local objectives are different from each other, their local optima, x1 star and x2 star, can be different from each other as well as from x star, which is the global optimum. So with this setup, let's consider two extreme cases. One where you just do one local update at each client, and another where you do a large number of local updates. So the large number of local updates is all, of course, better in terms of communication because your edge clients are talking less frequently with the central server. But then let's see what effect it has on the conversions. So in the tau equal to 1 case, you start off with the global model, and then these clients, they make one local step each, so shown in the solid blue arrows, and their updated models are averaged to get this dotted arrow, which shows the progress of the global model. And if we repeat this, you can see that eventually this global model is moving towards the global optimum. So we can actually formally show this. This algorithm ensures that the direction of movement of the global model is towards the global optimum. As long as you choose a small enough learning rate and all the clients participate, we can show that this is actually equivalent to mini batch SGD, and we get consistent conversions to the X star, which is the global optimum. But now if we go to the other extreme case, let's say each of these clients takes a large number of local steps, then their models will reach close to their own local minima. And when we average them, this is the global model that we get. So it seems to be making progress towards the global optimum X star. But then if you look at the second communication round, again, both of these clients will move towards their own local optima. And when we average them, we can get stuck somewhere here, which is the average of the local optima, rather than moving towards the global optimum. So this is at a high level, the problem that is caused by data heterogeneity combined with the fact that we are communicating less frequently. So the more local updates you do, the more these client models will drift away from each other, and then that will lead to an error in the final model that we get, the error being that it doesn't match with the global optimum. So more formally, actually several works in the recent literature have quantified this effect of tau on the convergence of the Fed averaging algorithm. And what they show is that if there is some bounded gradient dissimilarity, as shown here, so there is a bound on the difference between the local gradient and the global gradient, as shown here. There are other ways to measure heterogeneity as well, but this is one of them. So with bounded gradient dissimilarity, the error, which is shown on the left-hand side, is bounded by the expression on the right-hand side. here. So this is the error after capital T communication rounds of the Fed averaging algorithm. So you don't have to understand all the details of these terms. The high level takeaway is that the first two terms come from stochastic gradient error. So locally at each node, you are sampling from the local data set and computing noisy gradient. So the error here comes from that. The error that comes because of data heterogeneity is this last term, which is called the client drift error. So you can see that it increases with the amount of gradient dissimilarity, and it also increases with tau, which is the number of local updates that is done at each client. So how do you mitigate this client drift error? There are actually several ways that are proposed in literature. So one of them, a simple way is to just set a small value of tau, the number of local updates, or a small value of eta, which is the learning rate. So if we do that, these client models won't drift away too much from each other, and that will avoid or limit this error. Another way is that we could adapt tau over rounds. So you could start off with a large value of tau, and as you get closer to convergence, you adapt it, you reduce it gradually such that this error term disappears towards the end. So this is a method that we proposed in one of our works, and some other works have also concurrently proposed similar methods. And another approach is to actually add a correction term explicitly. So whenever these client models go in different directions, you try to pull them back towards the global model by adding correction term, either using some proximal update or using control variates, which are proposed in this scaffold work. So overall, these methods do work well at limiting client drift, but a drawback is that they can slow down model progress and often incur additional communication and computation cost. So with that additional cost, we can limit client drift error and actually achieve good convergence of the federated averaging algorithm. So although this problem is kind of solved in theory, there are still some interesting open questions that are left to address. The first question is that it appears that in practice, even if you use just regular Fed averaging without any of these correction techniques, it works pretty well, and it often outperforms SGD and these corrected versions of Fed averaging. So it turns out that the client drift error, although in theory it is a big problem and it increases with tau, in practice, it often doesn't affect the convergence that much. So this phenomena is not yet well understood. Maybe the reason is that, maybe the reason for Fed averaging doing well is that the gradient dissimilarity assumption, which is often made, is too pessimistic. So this is still a problem that requires more investigation. So in one of our ongoing works, we are trying to understand this by proposing a different data heterogeneity measure, and then trying to show that maybe under that data heterogeneity, Fed averaging itself performs pretty well, and you don't need to explicitly try to limit the client drift error. Another open question is that if you look at this error expression, this term seems to be the problem because it's like added on top of the stochastic gradient descent error. But if you look at this term, it may not actually be the dominant term. So it has this eta square. And if eta is small enough, then this term is much smaller and it decays faster than the other terms in the bound. So, and especially in this bound, we are assuming that all M clients participate. But if only a subset of the clients participate, then there is actually an additional term which is dominant, and it decays at a slower rate than this client drift error term. So in practice, especially when you have partial participation, maybe client drift is not a big problem. And what we really need to tackle is that additional term, which is the partial participation term. So that is what I'm going to talk about next when we discuss communication heterogeneity. So as I mentioned before, in every round of training, instead of all the clients participating, only a subset CM of the clients actually participate. So let's see what happens when we have such partial participation. How does it affect the error? So if a fraction C of clients chosen uniformly at random participates in each round, then the error after T communication rounds can be given and can be bounded as shown here. Again, in this bound, the first two terms come from stochastic noise in the gradients used for the local updates. And this last term is the client drift error term like we saw before. But now we have this additional term, which is called the partial participation error. So you can see that it depends on capital C, which is the fraction of clients that participate. And if C is equal to 1, then this term just disappears. But if C is smaller than 1, which is the case in practice, then this term becomes dominant. And to see that, we can see that if we set the learning rate appropriately, that is it decays at an appropriate rate with the number of communication rounds, then the order of these three terms is as shown here. So the first term is the stochastic noise, which decays as 1 over square root of T. The second term, which is the partial participation term, also decays at the same rate, whereas the client drift error decays at a faster rate. So you can see that the partial participation dominates over the client drift error term. So our goal now is to try to limit or eliminate this partial participation error term. So how do we do that? Like, we cannot force all the clients to participate. We have to just make do with the fact that only a subset of them are going to be available in each round. But what we can use is that whenever a client participates in two consecutive rounds, there is some temporal correlation between the gradients that it sends, because the global model does not change that much. So the gradients that this client would compute may not change that much across rounds. And this temporal correlation can be exploited to limit or eliminate this partial participation term. So that's the idea that we use in our work called FedWar, which was presented at UAI this year. So what we do is that whenever clients that are participating send some updates, that is, they send their updated model, we just store it in server memory. So this delta shows the model update that is stored in memory. And the server memory is denoted by yi. So the yi becomes equal to delta I whenever a client participates, and whenever it does not participate, it just maintains its previous value for that client. So for each of the clients, you save one vector in memory corresponding to the model update sent by that client. And then what we can do is when we have to update the global model, we use a combination of the fresh updates that are sent by the participating clients and these updates that are stored in memory. So we can combine both of them and compute this variance reduced update. So the variance reduced update, you can see here, it is the sum of the average of whatever is stored in server memory, and then it also considers the difference between the fresh updates and what is stored in server memory for the participating clients, which is the first term. So it's not simply an average of everything that's stored in memory and the new updates, because that would be a biased estimate of the full gradient. So this expression that I'm showing here is an unbiased estimate of the full gradient. So if we use this variance reduced update to get a new version of the global model, then we can show that it is actually possible to eliminate this partial participation error term. So by using this update in FedWarp, we can get rid of this term and only get the remaining terms in the error. So this is the main idea of overcoming partial participation by leveraging the temporal correlation in updates across the clients. And an advantage of this method is that it does not modify the local training procedure at these edge clients. So they can just do local updates normally and send them back. The server is the one that is maintaining the memory and then trying to reduce the variance in updates by using the information that is stored in memory. So because it does not modify the local updates, this method can be combined with other methods that mitigate client drift. So those other methods that I mentioned before, like scaffold or fedprox, could be combined with this algorithm to eliminate both partial participation error as well as the client drift error. So one might also think that isn't it too expensive to maintain in the server memory one vector for each client, because now you have thousands of clients. So that is true, like the server memory can be a problem in practice. So to reduce the cost of server storage, we propose a modified version of this algorithm, which is called clustered FedWarp. Where it, instead of storing one value in memory for each client, it clusters the clients together and then only maintains a single state per cluster. And this clustered version does almost as well as the regular version of FedWarp, as shown in these experimental results. So the red curve and the green curve show the regular FedWarp and the clustered version of FedWarp. And the other curves show the Fed averaging algorithm, which is in the yellowish green. And the blue algorithm is another recent method that uses server memory, but it uses biased updates rather than unbiased updates. And scaffold is that method which limits the client drift error term. So we can see that FedWarp outperforms Fed averaging as well as several of these client drift mitigation error terms, and using this more efficient clustered version does not lead to much of a loss in performance. So that is how we can tackle the variance coming from partial participation of clients. Now let me briefly mention something about client selection. So far, we assume that this C fraction of clients that participate in each round are chosen uniformly at random from the whole population. And this kind of uniform or unbiased selection of clients is beneficial in the sense that it allows us to extend several of the prior results for the full client participation setting to this partial participation setting. And several of the algorithms can also be just generalized. But it turns out that maybe it is better to not use unbiased client selection. What if we can smartly select which clients will be chosen in each round and potentially improve the performance? And the reason that we have that intuition is that whenever we select a subset of clients, that induces some surrogate objective function, which is the sum of the local objectives of these selected clients. And if you look at the global objective, which is the sum over all the clients, clients which have a higher value of loss, that is fi of x is large, dominate this local objective. So we could potentially improve the convergence by biasing towards clients that have a higher loss. So to illustrate that, let me show an example again with two clients. So suppose you have two clients which have the local objectives F1 and F2 shown here, and the global objective, which is a weighted average of these, is f of x. Now, if we do an unbiased random selection where you choose just one of these clients at random in each round, then we can start off from some point, and then in every round, because we choose one of these objectives, we can either move downwards along the green curve or the blue curve, and then we just switch back and forth between them. So you first, let's say, select client 2, then you move downwards along F2. And now if we switch and select client 1 in another round, then you move along the blue curve, and this process goes on. And because there is a randomness in client selection, you could potentially cycle back to a point that is close to the initial point, but eventually we will converge to the minimum of the global objective function. On the other hand, if we do a biased selection where we always choose the higher loss client, then we keep on moving downwards along just one curve until the two curves cross each other, and only then we move along the other curve. So this method, you can see that it avoids that kind of cycling effect and it gives faster convergence. So that is the high-level motivation behind doing smarter client selection. And we can formalize this and try to show how the selection strategy affects the convergence. So I'm going to skip the details of the math here, but the main idea is that we can compute something called the selection skew of a strategy to choose the clients. And that skew is denoted by this parameter rho. So if that skew is equal to 1, then we have unbiased selection. If it is greater than 1, then we are biasing towards higher loss clients. If it's less than 1, we are biasing towards lower loss clients. And we can show that the error after T communication rounds is given roughly as shown here, where the first term, the convergence rate, increases with this selection skew. But as you have more and more selection skew, there is also a non-vanishing bias term, because now the surrogate objective function that we have is a biased version of the global objective. So there is some cost that we pay. We get faster convergence, but we might get a higher error floor if we introduce a skew in the client selection. So based on this idea of biasing towards higher loss clients, we propose a client selection strategy, which is called power of choice selection. So here, what we do is we can first sample a candidate set of clients uniformly at random or in proportion to the local data set size, estimate their losses, and then select the CM clients with the largest local losses. And the size of the candidate set D here will control how much bias is there in the selection. So if we just set D equal to CM, then it's just unbiased client selection. And as we increase the value of D, you're skewing more and more towards the higher loss clients. And this idea has been used in single node SGD in the past successfully, although we are the first to apply it to the client selection setting. So we can show that in practice, this works pretty well. So the blue curve here shows the power of the client selection strategy, and it converges faster than just random selection. But at the end, you can see that it gives a slightly higher error flow. So, and another potential drawback of this strategy is that it might require additional communication because you're sampling some candidate set of clients and then estimating their local losses and then subsampling among them. So to overcome these limitations, we can propose some communication and computation variants of this strategy, which work almost as well as the original strategy. And we can also propose adaptive versions of the algorithm where this size D changes over time, so as to ensure that we get fast conversions, but we also don't suffer from a higher error flow. And interestingly, these kind of bias selection strategies do even better when there is more data heterogeneity in the system, because biased selection gives a even higher advantage in that setting. So summarizing, we propose this loss-aware client selection strategies, but a couple of open questions are that, what if we just use some kind of round-robin selection? Can it still do better than unbiased selection? And initial results indicate that the answer is yes, but we're still working on this. And another question is, can these kind of loss-aware selection strategies also improve fairness in addition to improving convergence? And initial experiments also indicate that yes, these client selection strategies can also give better fairness in terms of giving representation to clients which may have too little data or rare data that is very different from the other clients in the system. So that was about communication heterogeneity. I think I have about 15 minutes or so left. So in the remaining part of the talk, I'll quickly talk about computational heterogeneity and then wrap up. But let me pause here in case there are any questions.
So actually there is a question. Somebody's asking, how do you select D in this power of D method?
Okay. So in the power of D client selection strategy, the D is a parameter that we can choose as we want. So you can choose D to be small if you want the strategy to be less biased towards high loss clients. And at the extreme, if you choose D as equal to CM, then you get back the original Fed averaging algorithm. But as you increase D, you're being more and more selective and you're biasing towards higher loss clients. So it's actually a free parameter that you can choose. And as you increase D, we can show that you get faster conversions, but then you also get a slightly higher error flow. So ideally, what we should do is start off with a large value of D and then gradually reduce it as you come closer to convergence. I hope that answers the question. Any other questions?
I think there are none right now, I think. And he said, thanks, he understood. I was happy with the answer.
Okay, sounds good. So in the remaining few minutes, let me talk about computational heterogeneity. So as I introduced before, what I mean by this is that the clients may do different numbers of local updates, or they may use different learning rates or local optimizers. And we want to understand how that affects the convergence and how we can mitigate this source of heterogeneity. So why is this heterogeneous local updates a problem? So we can see that again through an example. So suppose we have a homogeneous setting where you have these two clients similar to what I described before, and both of them, they do the same number of local updates. So both here do two local updates each. And in this case, in the heterogeneous setting, one client does many more local updates than another client. So if we have this kind of heterogeneous local updates and we still naively average the updated models just in proportion of the local data set sizes, then the global model, you can see xt+1, gets skewed towards the client that does more local updates. And this skew is consistent across different communication rounds. So in every communication round, you'll keep on moving or biasing towards the first client because it did more local updates. And this kind of skew cannot be easily fixed by the techniques that we used to tackle data heterogeneity, because those are just going to slow down the convergence. Those techniques, they will pull back the client models towards the global model, and they'll pull back both the models. So they are going to slow down the overall convergence. So in our work, which we called FedNova, or federated normalized averaging, we analyze a generalized version of the Fed averaging algorithm, and we actually try to identify the root cause of this problem. So the root cause is that in the homogeneous setting, by doing these local updates, as long as you set a small enough tau and a small enough learning rate, you are still optimizing the true global objective function. But if you do this kind of heterogeneous local updates and then naively average them, then we end up optimizing the wrong global objective. So it's actually a mismatched objective where the weight given to the ith client is proportional to the number of local updates done by that client. So how do we make sure that this objective that we are optimizing using Fed averaging is not mismatched and it actually is equal to the global objective? So intuitively, the answer is that we just need to fix the aggregation weights, which is the way you're averaging the updated models. And that's exactly what we'll do. But the question is, how do you set those aggregation weights properly so that the mismatched objective turns out to be equal to the global objective? So to understand and identify what exactly these aggregation weights should be, we have to consider a generalized version of the Fed averaging algorithm, and then that reveals the correct setting for these aggregation weights. So suppose you have the Fed averaging update, which is just the plain update shown here that averages the model updates in proportion of the data set sizes. We generalize it in two ways. The first is that instead of considering the update delta as just the sum of the sequence of gradients that is computed at that client, we consider that it's a linear combination of the local gradients. And this allows us to subsume several existing optimization methods. So by setting these linear combination weights, we can subsume algorithms such as the regular Fed averaging or Fed prox or momentum, etc. The second generalization is that the central server, instead of just taking a weighted average of these delta i's, we force it to take a weighted average of normalized versions of delta i's. So this is just like an adjustment in the weights of the averaging. So instead of averaging delta i's, we are going to average di's, which are normalized versions of these delta i's, where this normalization factor in the denominator is the L1 norm of that AI vector. And then we also allow this PI to be set as some WI, which can be chosen freely. So with this generalized version, the main idea is that instead of averaging these blue arrows, which are the total local updates, we average these green color arrows, which are normalized versions of these updates, where the normalization factor is the number of local updates that is done at that client. And if we do that, then we can make sure that the global model is not moving in the direction of the client that does more local updates. So I'm going to skip some of the details here in the interest of time. I'll be happy to chat about them offline. So with this generalized Fed averaging algorithm, we are actually able to subsume several existing methods, including Fed averaging, Fed prox, momentum SGD, etc. So this idea of normalized averaging can be applied to several existing methods that are there in practice. And the Fed Nova algorithm, what it simply does is that instead of averaging these blue color arrows or the total accumulated gradients, it's going to normalize them, compute these green colored arrows, and then average them instead. So you can see that the direction of this arrow changes from the solid blue to this orange arrow, and that orange arrow is the corrected version because of the normalization. And we can show that this corrected algorithm actually optimizes the true global objective function. So let me show a few experimental results. So these are for a synthetic data set. They show that by correcting the averaging, Fed Nova can get much faster conversions to the a much lower error floor than Fed averaging or Fed prox. And as I mentioned, it can be combined with different client optimizers. So by just changing the averaging method as compared to Fed averaging, we can get an almost 8 to 10% increase in test accuracy if you go from the first column of this table to this column. And finally, so far I talked about just the clients doing vanilla local SGD. But often if we use adaptive optimizers like AdaGrad or Adam, those give faster convergence. But currently, these have been used only on the server side. So at the server, when you aggregate these local updates, you could use something like Adam or AdaGrad over there. They are not used at the clients to do the local updates because that causes heterogeneity and inconsistency across clients, because if you use them for local updates, then the local progress depends on local Hessians, which are heterogeneous across the clients, and then that can cause inconsistency problems, similar to what we have if you did heterogeneous local updates. So in another work, we show that we can correct this kind of heterogeneity and get the advantages of local adaptive optimization without the problems of convergence. So if you have Fed averaging, it's given in blue here. Just regular client AdaGrad without any correction gives the green color curve, which converges fast at the beginning, but leads to a higher error floor because of this consistency issue. But the corrected version of AdaGrad gives this red color curve, which gives much better conversions than both Fed averaging and the uncorrected version. And you might wonder why are there these jumps in the curve? So those jumps correspond to places where you decay the learning rate. So that's why we have the curve just flattening out at some point and then decaying again. So let me summarize. In this talk, we mentioned different sources of heterogeneity in federated learning. So the key takeaway is that we don't want to just force all the clients to behave homogeneously, because inherently there's data heterogeneity, communication heterogeneity, and to allow the system to be scalable and flexible, we need to allow the clients to be heterogeneous. But we can design algorithms that can ensure fast conversions in the presence of such heterogeneity without adversely affecting the communication complexity, computation complexity, or slowing down the error convergence. So that was the summary of the talk. Now, let me just mention a few other interesting directions related to heterogeneity that I did not talk about today. So one form of heterogeneity that we did not consider is model heterogeneity. That is, the model itself, a large model, may not fit in each edge client's memory. So you might want to use moderate size models for clients that have slightly lower local memory, and even smaller models for clients that have very low local memory and computation costs. And this kind of model heterogeneity calls for different aggregation methods. So you cannot just average models that have different sizes. We need some methods such as distillation to do that. So considering model heterogeneity is an interesting ongoing line of work. Then considering concept drift or data drift. So the data, we assume that it is static. The distribution does not change over time at the clients, but in practice, it does change over time. And considering data drift is an open question that needs more investigation. Then personalized federated learning, like I mentioned before, is a whole sub area that is still, there's still a lot of ongoing work on it. And also, finally, I want to mention an open direction where we want to incentivize clients to participate in the federated averaging framework. So if a client's local data set does not match well with other clients, it may be incentivized to just leave the framework and not participate. So how do we make sure that we get all the clients to participate and get the benefits of federated learning at the global model? So with that, let me stop, and I'm happy to take questions. I've also listed the archive links to the papers that I mentioned here. And that's it. Thanks.
Thank you, Professor Joshi, for an informative talk. We can take 1-2 questions more.
I had a question related to the choice of the weights PI. I still can't get the rationale behind having this PI proportional to the data size. And could it be possible to generalize this selection of PIs to the, your adaptive or the other mechanisms that you talked about for handling heterogeneity? I think in FedNova, you talked about adjusting PIs, but
Right. So, okay, let me answer this question in 2 ways. So firstly, how do you set PIs in the global objective function itself? So in this picture, I'm saying that the f of x is equal to an average of FIs in proportion of PI, where PI is the fraction of data at the ith client. So setting for the objective function itself, it makes sense to set PI as the data size fraction, because what we are trying to emulate here is a framework where if we had transferred all the data to the cloud and done model training centrally, we get some model. We want to come as close to that as possible while still keeping the data distributed. So if you want to do that, then it makes sense to set PIs as equal to the data set size. But when you run the algorithm itself, when we are taking the average of the models during the operation of the algorithm, you could choose PIs differently over time. So there is flexibility there. And in FedNova, as we saw, we adjust them to account for the fact that if one client does more local updates, then its weight needs to be adjusted so that overall we are still optimizing the global objective function that we defined at the beginning.
So I had a related question. Are there any examples where non-updation of these models is catastrophic? Where do you have examples where it's really critical to have these updates either at an individual client or at the collective global optimal level?
I think I didn't get the question because like why the
one
goal is
example.
to find goal is to update the model, right, and minimize this objective function. Like why would you want to not update it?
One example you gave was the word prediction, but are there any use cases where not updating the global model, either at a client level or at a collective model, is really catastrophic? Like the predictions go horribly wrong and there's some severe
Okay,
consequences.
I see. So maybe what you're asking is what if the updates go wrong? Like if let's say you have only a small fraction of clients participating and they have some really rare data that just disrupts the progress of the global model.
Right.
So those kind of phenomena can happen. In fact, like there is another line of work within federated learning which tries to tackle adversarial clients, where a client might be sending poisonous updates so as to just sidetrack the convergence of the global model. And how do you try to limit the effect of such adversarial updates? So that is also an interesting line of work.
Thank you.
Any other questions? Thanks again.
I had one last question. So, is there a possibility of making this update process hierarchical, where you only update a subset at a intermediate node, and can that help with the overall process of handling heterogeneity?
Yeah, that's a good point. And yes, you can do that, and that can allow you to, in fact, hierarchically set models for different clusters of clients. So instead of having this kind of star topology where you have a central server that's connected to all the clients, you could have intermediate levels of edge servers that are connected to different sets of clients, and then each edge server has a different global model, and then these models are then aggregated in the cloud. So that will allow also some personalization for of the model for different clusters of clients. So that's a valid setup, and these algorithms could be extended to that hierarchical setting.
Thanks.
Thank you, Professor Joshi. The link to the slides will also be posted on the webpage. Thank you and have a great evening.
Thanks, everyone. Thanks again for the invitation.